Preparing for a software engineering at PagerDuty interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a reliable incident event ingestion pipeline for PagerDuty? I would design the pipeline as authenticated ingestion, normalization, deduplication, routing, notification, and audit stages. Producers provide idempotent keys, while durable queues absorb bursts. Workers use tenant-aware partitioning and exponential backoff. I would persist event state separately from delivery attempts, expose metrics for lag and failure rates, and provide replay tooling. The central trade-off is latency versus durability. For critical alerts, I would favor durable processing and make eventual delivery visible through status APIs. While answering, cover authenticated ingestion, durable queues, schema validation, idempotency, partitioning, backpressure, retry handling, tenant isolation, observability, and replay capabilities during downstream outages. Question 2. How would you make an incident creation API idempotent? I would require an idempotent key for every incident creation request. The service would atomically store that key, a request hash, and the resulting incident identifier before returning success. A retry with the same key returns the original response, while a different payload produces a conflict. The record needs a carefully chosen retention period, and concurrent requests must share one transaction boundary. This protects clients from duplicate incidents when networks fail after successful writes. Make sure to cover client-supplied idempotent keys, request fingerprints, durable storage, atomic writes, expiration policies, repeated responses, concurrent requests, and behavior when identical keys carry different payloads. Question 3. How would you implement alert deduplication without hiding distinct incidents? I would deduplicate using a stable, customer-controlled key derived from service, resource, and failure type rather than raw message text. An active incident with that key would receive additional events, update counts, and preserve the first occurrence. Once resolved, a later event should create a new incident. I would support configurable grouping windows and expose correlation metrics. The design must favor transparent false negatives over silent merging of unrelated failures. In your answer, discuss deduplication keys, time windows, service context, state transitions, explicit resolution, collision risks, customer configurability, and metrics that reveal over aggressive or ineffective grouping. Question 4. How would you design notification fanout for email, SMS, push, and phone calls? I would create one durable delivery task per recipient and channel, then process tasks asynchronously through channel-specific workers. Each worker records attempts, provider responses, and next retry time. Escalation logic should advance only when policy conditions are met, not merely when a request is queued. Provider outages require bounded retries and alternate providers where practical. I would preserve ordering for one incident while allowing unrelated incidents to proceed independently, preventing a slow channel from blocking the system. Be sure to mention asynchronous fanout for channel providers, delivery state, rate limits, fallback policies, provider failures, ordering, deduplication, escalation timing, and user-visible delivery history. Question 5. How would you prevent one large customer from overwhelming a multi-tenant alerting service? I would enforce quotas at the edge using tenant-specific token buckets, allowing controlled bursts but limiting sustained volume. Internally, queues would be partitioned or scheduled with weighted fairness so a large customer cannot consume all workers. Events exceeding limits should receive explicit responses or enter a bounded overflow path. I would monitor per tenant latency, drops, and queue depth. Capacity planning would use aggregate demand plus isolation headroom, rather than average traffic alone. Focus on tenant-aware quotas, admission control, queue partitioning, weighted fairness, burst allowances, backpressure, noisy neighbor metrics, and clear handling of rejected or delayed events. Question 6. How would you evolve PagerDuty APIs without breaking existing integrations? I would prefer additive changes, new optional fields, stable resource identifiers, and documented defaults. Breaking behavior belongs in a new version or explicitly negotiated media type. Every endpoint should define pagination, error formats, and retry guidance consistently. Consumer contract tests and production usage metrics would identify risky clients before deprecation. I would announce timelines, provide migration examples, and retain old behavior long enough for integrations to move safely. Cover backward compatible additions, explicit versioning, contract testing, deprecation windows, pagination, stable error schemas, observability, migration documentation, and compatibility with automated customer integrations. Question 7. When would you choose strong consistency versus eventual consistency in an incident management system? I would use strong consistency for transitions that must not conflict, such as resolving an active incident or advancing an escalation step. Eventual consistency is appropriate for dashboards, search indexes, analytics, and replicated activity feeds where slight staleness is acceptable. The boundary should be explicit in APIs and user interfaces. For replicated state, I would include versioning, reconciliation, and audit history. This balances correctness for operational actions with scalability for read-heavy experiences. In your answer, distinguish user-visible correctness from scalable propagation, and discuss incident state, notification decisions, read replicas, stale data, reconciliation, and clearly communicated consistency guarantees. Question 8. How should a notification worker handle retries, timeouts, and downstream provider failures? I would classify failures first. Validation errors should not retry, transient network failures should, and unknown responses require idempotent reconciliation. Each attempt gets a strict timeout and bounded exponential backoff with jitter. A circuit breaker prevents an unhealthy provider from consuming all workers, while a dead letter queue preserves exhausted tasks for investigation. I would track delivery latency and failure rates by provider. Retries improve resilience, but unlimited retries create congestion and duplicate risk. Discuss bounded exponential backoff, jitter, timeout budgets, retry classification, dead letter queues, circuit breakers, idempotent provider calls, and alerting on persistent delivery degradation. Question 9. What observability would you add to an incident processing service? I would instrument each event with a correlation identifier spanning ingestion, routing, and delivery. Core metrics would include accepted and rejected events, queue age, processing latency, notification success, retry counts, and incident state conflicts. Structured logs would capture decisions without leaking sensitive payloads, while traces would expose cross-service delays. Dashboards should separate platform-wide and tenant-level signals. Alerts should reflect user impact and error budgets, not every isolated exception. Make sure to cover structured logs, metrics, distributed traces, correlation identifiers, queue lag, delivery latency, error budgets, tenant dimensions, cardinality control, and actionable alert thresholds. Question 10. How would you define and use SLOs for an alerting platform? I would define SLOs around customer outcomes. Accepted events should become visible within a target latency, and eligible notifications should be attempted or delivered within another target. I would measure availability and latency separately, segmenting by channel when useful. An error budget turns reliability into an engineering constraint. Rapid burn triggers mitigation, while healthy budgets permit change. I would exclude invalid customer requests but never hide internal processing failures behind broad exclusions. Be sure to mention availability, ingestion latency, notification latency, delivery success, meaningful user journeys, error budgets, burn rate alerts, exclusions, and trade-offs between reliability and feature velocity. Question 11. How would you model incidents, services, escalation policies, and notification attempts in a relational database? I would keep services, escalation policies, users, incidents, responders, and delivery attempts as separate entities with foreign keys and carefully designed indexes. Incident state changes would be transactional and recorded in an append-only audit table. A uniqueness constraint could protect active deduplication keys within a service. High-volume delivery history may need partitioning or separate storage. I would preserve immutable facts while allowing current state tables to remain efficient for operational queries. Cover entity boundaries, foreign keys, immutable audit records, incident state transitions, indexes, uniqueness constraints, transactional updates, retention, and separation of operational data from high-volume delivery history. Question 12. Where would caching help in PagerDuty-like services, and how would you avoid stale operational data? I would cache relatively stable data such as service metadata, routing configuration, and user preferences, using short TTLs and event-driven invalidation where feasible. I would not rely on a cache for authoritative incident transitions or escalation decisions. Read-through caching with request coalescing prevents stampedes, and the service must continue safely when the cache fails. Metrics should show hit rate, evictions, latency, and stale read incidents. Correctness-sensitive paths should query durable storage directly. Discuss caching policy and scope, invalidation, TTLs, stampede prevention, read-through patterns, consistency-sensitive exclusions, cache failures, and metrics for hit rate and stale responses. Question 13. How would you prevent race conditions when two responders update the same incident? I would model incident changes as validated commands against a versioned record. Each update includes the version it read. The database accepts it only if that version remains current. Conflicts return a clear response so the client can refresh rather than silently override another responder. State transitions must be checked inside the transaction, and commands should be idempotent. Last write wins is unsafe because a stale resolve or acknowledge action can erase a newer operational decision. In your answer, explain optimistic locking, version checks, transactional state machines, idempotent commands, conflict responses, ordering, and why last write wins is dangerous for operational state. Question 14. How would you secure APIs handling incident and user data? I would authenticate requests with short-lived tokens or securely managed API keys, then authorize every resource access against tenant and role boundaries. Input validation, parameterized queries, rate limits, and replay protection reduce common attack paths. Data would use encryption in transit and at rest, with secrets stored outside source control. Audit logs should capture security-relevant actions without exposing payloads. I would also test isolation explicitly, because cross-tenant access is a critical failure. Focus on authentication, authorization, tenant isolation, least privilege, secret management, encryption, input validation, audit logging, abuse prevention, and avoiding sensitive information in logs or error messages. Question 15. How would you merge overlapping maintenance windows or incident intervals efficiently? I would normalize timestamps first, reject intervals whose end precedes their start, and sort intervals by start time. Then I would scan once, extending the current interval when the next start overlaps. Otherwise, I would omit the current interval and begin another. Sorting costs O, n log n, and the scan costs O, n. I would define whether adjacent windows merge, use UTC internally, and test empty, nested, duplicate, and boundary touching intervals. Mention sorting by start time, linear merging after sorting, inclusive versus exclusive endpoints, complexity analysis, malformed intervals, time zone normalization, and tests for nesting and adjacency. Question 16. A customer reports delayed notifications, but dashboards look healthy. How would you debug it? I would first identify affected tenants, channels, regions, and time ranges rather than treating the report as a generic outage. Using a correlation ID, I would trace ingestion, queue wait, worker execution, provider response, and client receipt. I would compare timestamps using synchronized clocks and inspect recent deployments or configuration changes. If one provider or partition is responsible, I would shift traffic or increase capacity safely. Finally, I would add a missing signal before closing the investigation. Cover symptom reproduction, correlation IDs, tenant and channel segmentation, queue timestamps, provider latency, clock synchronization, tracing, recent changes, sampling limits, and safe mitigation. Question 17. What testing strategy would you use for an incident routing and notification platform? I would unit test routing rules, state transitions, retry classification, and authorization boundaries. Contract tests would protect integrations with event producers and notification providers, while integration tests would exercise queues, databases, and transaction behavior. I would add property-based tests for deduplication and interval logic, then inject provider failures, timeouts, and duplicate messages. Load tests should model bursty tenants. A small end-to-end sweep validates the critical journey, but tests must remain deterministic and observable. Be sure to include unit tests, contract tests, integration tests, property-based cases, fault injection, end-to-end scenarios, idempotency checks, load testing, and production-safe validation. Question 18. Tell me about a time you took ownership of a production reliability problem. In one service, queue latency repeatedly breached our target during traffic bursts. I quantified customer impact, traced the bottleneck to uneven partitioning, and coordinated a gradual repartitioning plan with operations. We added backlog alerts, load tests, and a replay-safe worker design before changing production. Latency dropped substantially, and recurring incidents stopped. The important lesson was to pair immediate mitigation with structural prevention. Ownership includes improving detection and reducing future operational load. Structure the response with situation, impact, investigation, decisive actions, collaboration, measurable outcome, and a lasting prevention mechanism rather than only describing heroic firefighting. Question 19. Describe a disagreement with a teammate about a design decision and how you resolved it. A teammate preferred synchronous notification delivery for simpler control flow, while I favored queues for resilience. I first clarified our latency and durability requirements, then proposed a small load test and failure experiment. The results showed synchronous delivery degraded sharply during provider slowness, so we agreed on asynchronous processing with a synchronous acknowledgement of acceptance. I documented the trade-offs and rollback plan. The discussion stayed productive because we tested assumptions instead of defending preferences. Focus on clarifying goals, separating facts from preferences, comparing alternatives, using experiments or data, documenting the decision, preserving trust, and revisiting assumptions when evidence changes. Question 20. How would you design a service that automatically routes alerts to the correct on-call responder? I would represent schedules as ordered rotation layers with timezone-aware intervals, overrides, and escalation delays. A routing request would evaluate the policy version captured when the incident started, ensuring later edits do not unpredictably rewrite history. The service would return the current target plus an auditable explanation, and cache stable schedule data carefully. If no responder is available, it should follow an explicit fallback policy. Deterministic evaluation and immutable versions make incidents explainable. Discuss schedules, escalation layers, overrides, time zones, policy versioning, calendar evaluation, fallback behavior, race conditions, auditability, and efficient handling of high-volume routing decisions. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.